Okay, so thanks the organizer for this very nice conference. I'm really happy to be here. And so this is a joint work with Marcus Whiteland, who is now in Loughborough University, Antoine Renard, who is there. And so with Marcus, we are the two advisors of Antoine, and also Bastien Mignotti, who was a master student at ENS Lyon. And so it was an opportunity to work on that because he did some internship in our group. And we were too busy to try working on that. And so his internship was the occasion to, work with Walnut. A bit like WIB with the student. So we had some intern to do some work with Walnut. So let's start gently. So I have a small game. So we will play on a graph, on a finite graph. The graph is without any cycle because I don't want any tie in the game. So there is no cycle. Okay, this is an acyclic graph. And so you lose the game as soon as you cannot move. So for instance, if a player is just here with this vertex, then you cannot move anymore. You cannot use any of the edges, so you will lose the game. So I have a blue player and a pink player, and let's say the pink player will choose the vertex where we start. And so the pink player say, okay, we will play from there. And so now it's turn to blue to play, and so blue has two options. He can either go there or there. And so let's say he play randomly, and so blue choose the right vertex and go there. And so now it's turn to pink to play, and again pink has two choices, and maybe pink will be clever. We will see that pink is clever because pink will choose the left vertex, and he goes there. And now we will see that the game is almost over because maybe pink play well because now blue didn't know, but maybe he will choose the one on the left. He go there, and then after some point, pink play here, pink go there, and blue is stuck. So blue has lost the game. So if you play a game like that, if you want to play against me, okay, the question is first, should you start or should I start? That's a good question, right? So let's see if we can decide that. And of course, we can decide. This is a finite graph. So how do you do? So start from the bottom, right? So here, for sure, if we start from here, I let you start because I win without doing anything. So these two positions are losing position. This is what I call the P position. This is the usual terminology. But then if these two positions are losing position, then you know that these three vertices will be winning position. Why? Because if you are any on these three blue vertices, then you know what to do. If you are here, you will play this move. Okay? And so you proceed like that. So now that you know that these guys are blue, so they are blue because there will exist an option that leads you to a P position, then you know that these two new vertices are now red. They are again P position. Why? Because there you're stuck. Whatever you do, all the options you have lead you to blue position. So you see, here, you are forced to go to a blue, and that's the same here. So you continue this way. So now that you color blue, red, you can continue this way. So now I know that these two guys will be blue, because you can play to a red. So now that you have new blue guys, you have more red. This one must be red because all the outgoing edges go to blue, and you continue this way. And finally, you see that the initial vertex with my example was colored in red. So it was a P position. So for sure, it was a clever choice for the pink player to let blue start, because pink knows that from that position, he eventually will win the game. Okay? And so, yeah.
Not allowed to choose.
Let's say that pink choose the vertex at the beginning. I mean,
Pink could have chosen one.
yeah, but then there is no fun. So, yeah, it would have won directly, yes, for sure. So, these red vertices are called the kernel of the graph. So the kernel of a graph, when the graph is acyclic, the kernel is always unique. And this is a set of vertices that has two properties. So the first one is that the set of red vertices is stable, which means that for any two red vertices, you cannot move between them. There is no edges between two red vertices. And the second property is that it is stable. What does it mean? If you are not with a red vertex, but with a non-colored vertex, you can always go in an element belonging to the kernel. So these are the two properties that I will use, stability and absorption, okay? And since Walnut will be involved, you see that they are really easy to express, okay? There is just some for all exists, so this is pretty simple logical formula, okay? So, now let's move to some other game, some combinatorial game, and one of the most famous one is the Wythoff game. And I discovered recently that Robert wrote a short biography about Willem Wythoff, and it is in Dutch. So the title is We Wait Willem Wythoff, and then something else that I forgot. The title is a bit long, but the title is WWWW, okay? Oh, okay. So I did not catch that joke. Thank you. And I learned that, okay, Wythoff got 2 PhD, one in chemistry, but also in math, and he also did work on graph theory and on polytope. So thanks you, Rob, for that. And so in Wythoff game, so you have 2 piles of token, and again, you have 2 players, and so that's the same. As soon as you cannot move, you lose the game. And so a bit like in the NIM game, you can remove whatever you want from one of the 2 piles of token, or there is an extra rule, and the extra rule is you can remove the same quantity from both piles, okay? And this, you can see this game exactly like a game on a graph. Like if you start with, let's say, 4 token and 2 token, then you build a graph like that one, and from that graph, you can define and find easily what are the losing position, what are the P position, and so on. So you can know if you would like to start or not, and you define a strategy like that. So it's a game on a graph if you want. And there are many known characterizations of this losing position. Like the first one involved the Fibonacci number, the golden mean. So you take the integer part of the multiple of the golden mean, and these are exactly the losing position of the game. That was the result given by Wythoff. Of course, if you like, the Fibonacci word encodes the P position. What do I mean by that? Is that if you number position in the word, you index the word from 1, 2, 3, and so on, you look at the first 0 and the first 1. They are in position 1 and 2. This is the first P position. Then you look at the second 0 and the second 1. They are in position 3, 5, and so on. So you can find back the losing position from the Fibonacci word. And there are other characterizations. And if you ask ChatGPT, he knows about the game, and he tells you how to play. And he even proposes you, okay, do you want me to write a small Python program to play with you and to find the losing position and strategy? And the answer is yes. But still, ChatGPT doesn't know everything because there is an extra characterization, maybe the nicest one, because it involves a numeration system. So Fraenkel proved the following result. You take the Fibonacci numeration system, and then you can easily find what are the P position, because you take a pair of integers, and so you write A using the Fibonacci or Zeckendorf numeration system, and you check if it ends with an even number of 0. That's the first condition. And then for the second component of the pair, it should be a shift of the first representation. So you add an extra 0. And these are exactly the P position of the game. So that's maybe the nicest characterization, especially if you think about Pierre Arnoux talk when he showed nice picture and nice animation, and there was problem because of rounding numbers. So if you take this first result, and it just take a few digits for the golden mean, and you take n large, so you make mistake when you will estimate what are the p positions. So it's much better to work with Zeckendorf numeration to get exactly this. And this is where I got my question. Okay, from this result, can I do something with Walnut? Because I have a numeration system, I have numbers written in a nice way, so can I use Walnut to do something with that? So it's a bit like Pierre Popoli's talk from yesterday, and it was not supposed to give you a talk yesterday, so I did not put your name there because you were scheduled for tomorrow. So anyway, so I could have. And in particular, I was not the first one to think about using Walnut with games. Robert also did a few papers about involving Walnut inside some of the game, like in this paper, okay? So in Walnut is based mainly on Buchy's theorem. And so roughly the idea is that if you can express something using first order logic and maybe a bit of extra ingredient, I don't want to talk about it, you have a decidable theory. So if you have a decidable theory, probably you have an algorithm to work with and you can decide stuff. And so mainly Buchy did this for integer base, but you can extend to other numeration system. The two ingredients are that, a bit like in Emily's talk, you need that the representation of the integer should be a regular language in the system you consider. And also addition should be computed by a finite automaton. So for instance, if you take Fibonacci number system, then I guess everyone knows that you get representation with no two consecutive one. So this is a regular language. And if you look at the triple of integer that you represent using Zeckendorf system, you have an automaton. So for instance, there is a description of this automaton in that paper. It's a 17-state automata for Fibonacci system, but you can also work with the Fruny normalization result to get this kind of result. So even if you don't speak Walnut fluently, this is just meaning, okay, I want an even number of 0. I want a left shift, so I can define p position. So I can define those p position. And then, since you can play symmetrically on both piles, I just do a symmetric stuff here. So I have my Fraenkel result that is implemented. But now remember the beginning of my talk. What do I need to check? I have this candidate, and to be the set of p positions, it should be stable and absorbing, right? But this is easy to write. Okay, this is the automaton produced by Walnut. So you see here, it's symmetric because maybe one pile is less than the other, okay? And for instance, 9, 15 is a p position, and you have the representation of 9 over here, and 15 is just the same with a shift, and you see that this guy ends with no 0, and 0 is an even number, okay? So this guy, you follow the right path into the automaton, and it is accepted. So I was saying, we just have to check stability and absorption. So these are the two formula I wrote at the beginning, and more or less you can read them here. You have to tell Walnut, I want to use the Fibonacci system. MSD just means I build automata with most significant digit first. You can also choose least significant digit if you prefer. And you see, for all p position, pq, and rs, so I take 2 p position, then you shouldn't have any move between those two. So either they are equal or there is no move. And similarly for the second property, you can write almost verbatim the formula just above. So you type that, you run Walnut, and it says true. So this is a proof of Fraenkel result in a different way. Of course, you don't know anything about the proof in itself, but you get the result almost for free. So as a summary, it works well because the rules are easy to express. You have a nice numeration system because addition is computed by an automaton. And my candidate is a regular language. And so in that case, everything goes well. Okay, I will skip many things from my paper because I have not enough time to deal with them. But one question we look quite usually is that I have a game, like Wythoff game, and people would like to know, okay, can I change a bit the rule in such a way that I keep the same set of P-position? Like, can I add new rules to the game? Can I remove some of the moves, but still keep the same set of P-position? And that's sometimes a hard question. So we work on that. So in particular, I have a paper with Fraenkel on that. And so we had a conjecture about the kind of move that can be added. And the conjecture was standing for 15 years. And I have a nice picture for this conjecture. Oh, not so nice, actually. It was nicer on my computer. And so this not so nice picture golden mean and 1 over the golden mean. So more or less, you can see P position over there. And this picture is supposed to be obtained by a bidimensional morphism. It's a morphic word. And my conjecture was it was a word obtained over a 26-letter alphabet. But with classical proof, I was stuck. But with Walnut, now I have a proof that the conjecture was okay. So, okay, you can really do some things that I was not able to do classically. But then Fraenkel continued to work. So for instance, he extended Wythoff game. So he changed the rule a bit. Remember, in Wythoff game, you can remove the same number of tokens from both piles, but you can relax that. Like now you can remove K and L token with respect to this condition. So there could be a difference, less than M, between the number of tokens we remove. But again, in that case, I just more or less copy-paste the same result as before, right? I just change the numeration system. And you see here that he shows that if you take this quadratic irrational number, and this is almost metallic number like in Sebastian's talk, except I have a 1 to start with and not an M. And so if you take this Ostrovsky numeration system, you have the same result. Oh, very nice. But if you have a quadratic number, quadratic will mean that the expansion is periodic, so an automaton can deal with such an expansion. This is a finite amount of data. And so again, in that case, you have a nice numeration system. Addition is computable by an automaton. And indeed, Shalit work on that. And so you can tell Walnut, use this Ostrovsky system. So I take, for instance, a square root of 2. So m equal to 2 there. And you can define the rule. You see, I can remove a and b with this kind of condition. So I fixed the parameter m to be equal to 2. And so again, can I prove this result using Walnut? Yes. This is exactly the same as before. So no need to do that again. That's the same proof, exactly the same. So we answer also other kind of question, just not to repeat the same stuff every time. So for instance, what is a redundant move? A redundant move is a move that you don't really need. You can avoid this move and still have the same strategy and still have the same set of P position. So it's easier to explain you what is a not redundant move. For instance, here, you see this position is a winning position. There are 3 options, but only this one will lead to a P position. So if it's your turn to play, you must choose this one. So for instance, this guy is not redundant, because if you remove this from your set of rules, you don't have the same strategy anymore. So you understand what is a not redundant move, and you just take the contraposition to get the redundant one. But this, again, you can express, right? It's easy to express in first-order logic. So you can do it quite easily. And so now we have an expression for non-redundancy, and then you just take the complement for redundancy. And so we can try to find what are redundant moves for this game. And so we get result. And exactly like in Whip's talk yesterday, we can prove the result, but each time for a fixed value of m. I cannot have a proof for all m at a time. So for m equal to 2, we know what are the redundant moves. We can do it for 3, we can do it for 4, but for 4 we needed 45 gigabytes of memory because the intermediate constructions are really huge. You build automata and automata that are bigger and bigger, and so you get stuck at some point. But still, doing this, we have a conjecture for an arbitrary m, exactly just like you. But then I need a real proof then. And so to finish with, we have a third kind of system because Fraenkel continue, and so he relaxed even more the rules. So now you can remove K and L token, but with this kind of condition, okay? So you have a new extra parameter S. And then again, there is a nice numeration system. You take this second order linear recurrence relation, you express numbers using this system, and more or less you copy paste the same result. I was just careful to change the date. It's a few years later. But they're still the same. And you know what? We are lucky. Because if you compute the characteristic polynomial, you get a Pisot number as a root. So you have a Pisot numeration system, and for Pisot numeration system, we know that addition is computable. So again, we can do exactly the same. Why? For exactly the same reason as before. Everything can be expressed using first order logic, and we have a nice numeration system. And just to give you a picture of the three systems I have considered, here it was Fibonacci. Then first generalization, you get one parameter, so now you have access to more letters in the representation. And next, with the second parameter, you have these new kind of edges that appear. But still, for Ostrovsky, Shalit did the job, and so we just tap Ost, and that's it. Here, we need to give to Walnut the automaton to compute addition. You can do it in two ways. For instance, Olivier with Nicolas Ollinger and others, they develop a tool for Dumont-Thomas numeration system, which is called Lycophage. And so he can build automatically this adding machine. Or I was quite happy to use the description given by Christian and Jacques Sakharovich in the Kant book, which is based on the zero automaton. So the zero automaton is just an automaton that recognizes all the expression of zero. So you use an alphabet using also a negative digit. And as soon as you can build this automaton, which will be finite because you have a Pisot number, then you just have to replace the label by triple of digits such that A plus B minus C is L. Because if you follow a path, at the end, if the result is 0, it just means that A plus B is equal to C when you read word. And so you do that. It's really easy to compute. It's a small Mathematica program. So you get the zero automaton, then you get the addition automaton. You still have to give also the automaton that check if you have valid U representation, and you get the same result. And also, Olivier and his co-author give this procedure. If you are not sure of yourself, you can check these 5 rules, and you are sure at the end that the automaton you provide really compute addition. So believe me, we really compute addition. So as a conclusion, the Fraenkel's combinatorial games with Walnut is a marriage made in heaven because everything was fine, really. So not only we get proof of all the results, but I was really happy to be able to prove one of my old conjectures. And from that, we can build also many new games. You just have the recipe here to build games for free, more or less. Of course, not everything is fine because just like in Whip's talk, we get proof only for fixed value of the parameter. So this is really challenging. Can you do it for every M or S, for instance? And also, as you have seen, state complexity could be problematic because there are theoretical results that prove that just Presburger arithmetic. So Presburger arithmetic is just n plus. You can get up to triple exponential results. So this explains why we needed 41 gigabytes of memory at some point. So even in theoretical setting, you can do things, but practically sometimes you cannot do. So we really had some wall. Like in particular, I have some question about Fibonacci games. I can write the formula, but I'm not able to do the computation because the Fibonacci adding machine is more complicated than the Fibonacci one. And so if you do exponential computation, then I'm stuck at that point. That's it.